Hello everyone, welcome to our debriefing session for the Manufacturing Hackathon. My name is Eliseu Pereira and I'm here alongside my colleagues Gil Gonçalves and Artur Freitas. Today we'll be discussing the work performed during the hackathon, focusing on the openZDM platform within the Sonai Arauco use case. So first, the contents of this learning tutorial are the following. First, a brief introduction about the openZDM project, the Sonai Arauco use case and the hackathon challenge. Then we will have a short presentation about Dinosaur, a tool that allows the development of reconfigurable and distributed cyber-physical systems. Then we will provide a suggested architecture based on Dinosaur to address the hackathon objectives. Finally, the last two presentations will describe two different proposed solutions. Let's begin by introducing the openZDM project, which is an innovative platform designed to enhance manufacturing processes, particularly focusing on solutions and technologies for zero-defects manufacturing in shop floors, playing an important role in reducing waste, improving efficiency, and integrating digital solutions into traditional industrial flows. The use case we will focus on is the Sonai Arauco scenario, a company that produces wood-based panels. Here the goal will be to implement a zero-defect manufacturing solution capable of predict and explain defects, as well as recommend new machine parameters to minimize their impact. The use case focuses on the process of decorative surface wood panel production towards a zero-defects manufacturing approach. In a nutshell, the process consists of coating a raw board into impregnated papers that are then pressed to the raw board surface using a combination of pressure and temperature. Now we will show a short video illustrating the process. After visualizing the video about the Sonai Arauco shop floor, we will introduce the hackathon. So the hackathon has the goal of predicting if a sample of data from the shop floor will result in a defective board or not, providing an infrastructure to integrate the data flow, store the data, execute the algorithms, and show the results and indicators. The simulated data from the shop floor is focused on the pressing section of the production process, where each 20 seconds is generated a sample containing data relative to the pressing process with the following data structure. We suggest that for implementing this solution, the utilization of Dinosaur to develop the code. For that, we will have next a short presentation introducing Dinosaur.
Hello everyone, my name is Eliseu Pereira. I'm from the University of Porto in Portugal, and my presentation is about Dinosaur, which is a tool that permits the reconfiguration in cyber-physical production systems. Starting with the agenda for that presentation, the first part I want to introduce a little bit of Industry 4.0, cyber-physical system, reconfiguration in that systems, and the ESC 61499, which is a standard to reconfigure cyber-physical systems. Then I will talk about the implementation of the Dinosaur itself and the integration with the other platforms. The third point is the test case scenarios that I have to present you. We have three different cases, and another one related to the performance evaluation of the tool, and the last one is related to the conclusions and the future work of this presentation and of this project. Starting with the introduction. As you probably know, the Industry 4.0 brings us several advantages, like the digitalization of the industrial equipment, which enables the connectivity between different kind of devices, and makes larger the networks and the cyber physical systems. Regarding that, it is important to have good tools to reconfigure the cyber physical systems in order to have, if you have a quick modification of requirements. For example, if you want to produce a new product, you don't need to go to the equipment itself and reprogram the equipment. You can perfectly configure the equipment from a remote computer and easily change your production targets, change your production line, and so on. Regarding that, there are different tools and programming languages to implement these kind of distributed cyber physical systems. One of them is the ESC 61499, which is an industrial standard. Another one is the Node-RED that permits the reconfiguration of devices also, and the Eclipse Cura. Focusing on the ESC 61499, that standard is composed by two different components, the development environment and the runtime environment. The development environment is basically where the user or the developer orchestrates his pipeline of tasks. Basically, his task, each task that you have here is a function block, which has event interface, where the events trigger different functionalities in that function block, and we have a data interface. Okay, so the user orchestrates a pipeline of function blocks which can perform a certain operation, like move a robotic arm and so on. Then the user maps each of the function block to one device that is running a runtime environment, and the IDE automatically sends the function block to that runtime environment to execute it. Okay. Focusing on the development environments that we have present right now, these are the three most common: the FD Bench, the FordiAC IDE, and the GART FDE. The most popular is the FordiAC IDE, which is a Eclipse-based tool, and have integration with the Fort FDE, which is a FDE implemented in C++. The other two IDEs have different features, but they they don't have so popularity in the community. Regarding the runtime environments that we have, some of them are implemented in C++, others in Java. Typically, the programming languages that that the runtime environment is implemented is the same that we need to implement the function blocks. So that could lead to some restrictions in the functionalities that we want to implement. For example, if we want to develop a classifier or a regression algorithm, is is easier to develop that in Python, and that could lead us to some disadvantages of using that kind of RTS. Another disadvantage is the third-party integration with regarding the Industry 4.0 and the interoperability between a large amount of devices. It's a limitation because we use every device to share information between every device that we have in the shop floor. And some of that tools of that runtime environments are achieved projects, which is also a big limitation, because if you have an error, you cannot share that error with anyone because the projects are achieved. Okay. Regarding the implementation of the dinosaur itself. Basically, the architecture that we have in the dinosaur, basically we adopt for the IDE as integrated development environment to drag our pipeline. And then we have integration with the dinosaur, which is a runtime environment that executes in embedded systems or, for example, other kind of computers. The dinosaur is implemented in Python, which permits us to implement algorithms for machine learning, communication easily, and have third-party integration with OpenCUA applications, which is good because in industry, most of the applications communicate through that standard. If you are curious to check the application, we have here the link, and you can go there and check tutorials and some other examples that we use to implement the dinosaur and so on. Some test case scenarios and so on. The dinosaur implementation itself uses a producer-consumer pattern based in threads, where each thread is basically a function block that consumes events and produces events. When a function block receives an event, he triggers its functionalities, executes, and then produces the output events that forward to the next function block that performs again and produces the outputs and sends the events to the next one. Okay, that is the execution model that we have implemented in the dinosaur. The function blocks, which are the tasks that we perform in our runtime environment, are implemented using two different files. A Python file where are implemented the functionalities, the code itself, and an XML file where we define the structure of the function block. Basically, the name of the events, the type of variables that the function block has as input and output, and so on. The next point is the integration with the 4DAC. The 4DAC is a different project. We integrate with them using TCP/IP sockets and XML messages. That communication permits from the 4DAC to create, stop, and delete the pipelines of function blocks in the RTA that is running that function blocks. This way you can drag or pipeline on the 4DAC IDE and deploy or pipeline of function blocks in the RTAs existent in the network. And another feature is to monitor variables and trigger events in the function blocks. Monitor variables, for example, imagine that you have executing this function block. You want to see the state of that variable. you and in the for the IDE are able to check that that value of that variable. Regarding the OPC-UA integration, as I said before, the OPC-UA integration enables the connectivity with external industrial platforms or applications. The data model that we have implemented permits to map each function block into a different category to organize better the information that we have. We have a device type, service, start point, and end point. The start point and end point are the types more related to protocols, where the data brings from another, for example, another function block that is another device. For example, you have a communication between MQTT or TCP/IP. You implement a start point or end point to bring data. Service is an example of a task, a predictive algorithm, and so on. And a device is basically a function block that runs permanently, reaching data from for example, from a sensor and so on. The data model permits also to store the actual state of the dinosaur. So, for example, if the dinosaur crashes, if we restart the dinosaur, we continue in the same state. The development process from the point of view of the developer to manage the whole system is composed by these 4 steps. Both four steps are performed in the for the IDE and in another platform if you want, for example, an IDE to develop the code. The first step is to develop the function blocks, the Python file, including the functionalities, and the XML file with the structure of function block. Then when the function block is created, you can orchestrate a pipeline, a different pipeline, connecting the function block between dependencies between them. The next step is to map each one of the function blocks to one different device. Okay, we have a key here, 2 different devices with 2 different IP addresses and ports. And then you can map each function block in the device where you want. Then in the for the IDE, you are able to deploy the pipeline and send the respective function blocks to each device that is running a dinosaur instance. The test case scenarios that I want to present regarding that platform. The first one is the collision detection in servo motors. We have here a robotic arm based in servo motors. As you can see here, this is a servo motor. This is another one. In this case, we collect data from the servo motors, collect the voltage, the current, the real and apparent power from the base and the shoulder robotic motors. We have here in this function block the data from the shoulder, the voltage, current, real power, apparent power, and here from the base motor. Then the next function block, using the data collected via serial port, predicts if the robotic arm is colliding with some object or not. Basically, for that, we use a classification algorithm, in this particular case, a random forest. And if it detects that we have a collision, he sends an event to the robotic arm controller that is performing some task to stop, to avoid being damaged because you are colliding to an obstacle. The next test case scenario, he has as components UR5 robotic arm and a 3D printed gripper that is composed by a Raspberry Pi, a servo motor, and 3D printed gripper also. In this particular case, we have 2 function blocks. One to move the robotic arm from one particular position, X, Y, Z, with particular rotation of the joints of the robotic arm. And we have also here a function block that is running on the Raspberry Pi of the 3D printed gripper that opens and closes the gripper using the GPIOs of the Raspberry Pi. Basically, this function block is running in the Raspberry Pi. This one is running in another computer that is controlling the robotic arm. So the operation that is made here, the gripper closes, moves up, moves down, gripper opens, moves up, moves down, and closes again, okay? The next scenario that I have is related to manufacturing applications. In this particular case, we want to simulate a production process. Each station of the process contains 3 different function blocks, and the products are simulated to pass through each station and being processed in each station. This example permits us to validate the scalability of the dinosaur. And regarding that scalability, we use that example to do the performance evaluation when we increase the number of function blocks to validate how the performance involves giving that data. So we conclude that basically the complexity of more function blocks causes more resource to be consumed. The rate of increasing is basically 18 function blocks by 1% of CPU usage, and that it's a scalable solution that you have here. If you have, for example, a very increasing usage, you can also split the function blocks between 2 devices to avoid that higher usage of resources.
After introducing Dinosaur, we'll present a possible architecture to address the challenges from this use case. We propose an architecture to ensure that data could be handled, analyzed, and provide predictions in real time. The suggested architecture to develop will integrate the following components: a data handler, which is a module to subscribe data from the MQTT broker and transform it according to the database schema, storing the data on the database; a database, which is the data lake to store the sensor data and predictions; the data analytics component, containing the algorithm that calculates useful information like the defects; the visualization component, containing the dashboards designed to show useful information about the sensor data and algorithm outputs. The component can use some dashboard technology like Grafana that integrates with the database. The data handler component, implemented using Dinosaur, subscribes to the MQTT broker, and every time that the function block gets a new sample, the following function blocks store the sample in the Postgres database. The Postgres database contains 2 tables, one storing the input sample containing the pressure, temperatures, among other variables. The other table contains the defect prediction values associated with a particular sample. Moving to the data analytics side, we suggest developing a predictive model using the k-nearest neighborhoods (KNN) algorithm. By training the model with the dataset provided during the hackathon, creating then a scalable solution. We exported the trained model and its color as pickle files and deployed them using Dinosaur. The deployment included function blocks that fetch stored samples, evaluate them with the model, and insert new predictions into the database. The final step of our process is visualizing the data. Through our data visualization solution based on Grafana, users can gain real-time insights about the performance of the manufacturing process, identifying defects and causes, as well as cumulative indicators, such as the total number of defects. With that, we finished the introduction, the Dinosaur presentation, and the suggested architecture part. Following, we will present the 2 proposed solutions.